Hello, geometry friends. In this video, I'll be looking at section 2.7, prove angle pair relations, and mainly what it's going to concern itself with is these four math conjectures. So this video is going to be mainly concerned with demonstrating why each of these things are true, with the exception of one, like I say, which we'll talk about in a moment. Trying to figure out what they're telling us, and then also finally, what you'll be doing on your own later is demonstrating how they could be used for actually solving some math problems. But right now, while we're still building our proof skills, and these are all relatively simple proofs, we'll be spending our time doing that in this video. Also worth noting is that proving theorems is a much bigger deal than just solving problems using the proofs that we've been doing, because if we're actually proving theorems, then we're essentially expanding our toolbox of geometric tools by adding new things to it. Like, a theorem is actually a pretty significant conjecture, much better than solving some random problem for x, because these are important things that actually are part of the foundations of geometry, and they're crucial skills, and to be able to demonstrate them, it really shows a deep understanding on our part, and it also helps with the fundamentals for things that follow from these. So first of all, let's see what all of these things conclude. There's something called the linear pair postulate, which this is not your first time hearing this. But the linear pair postulate is the thing that says angles of a linear pair are supplementary. And if you remember what a linear pair is, this isn't too surprising. A linear pair would be like angles 1 and 2 here, that when taken together, they make a straight line. Therefore, it makes sense to say that they're supplementary, because the angle addition postulate would have them equal a straight angle, which is 180 degrees, and then there you go. Number 2 here, right angle congruence theorem. This is exactly what it sounds like. It says that all right angles are congruent to each other. That barely sounds like a theorem because it sounds so not important. But the actual steps of saying that right angles, well, they're all 90 degrees, and if they're all 90 degrees, then all their measures are equal to each other, and all if their measures are equal to each other, then therefore they're congruent. That's tedious. We could just sum that up by saying the theorem says they're all congruent to each other. I've taken a shortcut with number 3. I'm cheating a bit, because what this is saying is it's essentially 2 theorems in one. If 2 angles are supplementary/complementary to the same angle, then they are congruent to each other. So suppose I have that, for instance, the measure of angle 1 is like 60 degrees. Let's look at the supplement part first. If I say that angle 2 is the supplement of 1, but also angle 3 is the supplement of 1, well, if 1 and 2 are supplementary, then it's got to be the case that the supplement of 60 is 120 degrees. 60 only has one supplement. It's 180 minus itself. If 3 and 1 are also supplementary, then measure of 3 has to also be 120 degrees, because again, there's only one number that when I add it to 60 gives me 180 degrees. So what this theorem is essentially saying is because because angle 2 is supplementary to 1, and angle 3 is also supplementary to 1, angles 2 and 3 must be congruent to each other, because their measures are both the supplement of angle 1. That is the congruent supplement theorem, and when you spell it out like that, it becomes obvious why it's called the thing it's called. Additionally, though, you can imagine how its like brother theorem, the congruent complement theorem, would work. It'd work the same way, except instead of the sum of the angles being 180, it would naturally be 30 degrees. It would naturally be 90 degrees instead. So these two would measure 30. The vertical angle theorem says that vertical angles are congruent to each other. We've not only talked about that in the past, but we've worked with it, and I think you can use that to solve, and you've been using it to solve for things in the past. So when I say that we are going to prove these things today, but then asterisk with the exception of one, the one thing that we're not going to prove is the linear pair postulate, because note how it differs from the rest of these. Theorem. This postulate, this conjecture, it being a postulate, means that we don't prove it, we use it for proving. Because with any of these theorems, for each of the steps, I could ask why. Why? Justify this. How do we know that? And eventually we have to get to some point where we just say, like, this is given information. And the linear pair postulate is something that we are essentially going to consider given. We know that this is true, or we're going to assume that it's true, and then use that as a building block for other things. So again, here's the linear pair postulate. If 2 angles form a linear pair, then they're supplementary. We would use it by saying the following: 1 and 2 are a linear pair, therefore 1 plus 2 is 180. If this were a 2-column proof, the justification I would have here is the linear pair postulate. This has no proof, like I just said, because postulates cannot be proven. The vertical angle theorem. This is something that, the year's 2020 right now, if you're watching this from the future. And in 2020, we proved this via Kahoot, via a game. That went quite well, I think. In And again, take a moment to maybe, with any proof really, you probably want to take a moment to observe what it's telling you, look at the thing that you're trying to prove, convince yourself in your head that it's true, and then go from there in terms of trying to justify it. If you need to, go ahead and pause the video, but I'm going to just power through this. We're going to start by noting that 1 and 2 are a linear pair, 2 and 3 are a linear pair. Therefore, their sum is 180. Their sum is also 180. I could actually do some like congruent supplement stuff here if I wanted to. We haven't talked about that theorem yet, but anyway. If I go down the line here, now that I've kind of got a game plan set up with linear pairs. 1 and 2 are a linear pair, that's given via the diagram. Therefore, they're 180 degrees as a sum. That's the linear pair postulate. I actually should have had degrees here. 2 and 3 are a linear pair. Guess what? That's also given to us. Guess what? This is all the same step. And then we get to a point where we're saying the measure of 1 plus the measure of 2 equals the measure of 2 plus 3. So how do we get that? We can say this green quantity is equal to 180. This green quantity is equal to 180. Therefore, via the transitive property, or substitution, I suppose, both would work, both of these green quantities are equal to each other. And then how do I get from this 1, 2, 3, 4, 5, the 5th line to the 6th line? It looks like what I've done is I've eliminated the measure of angle 2 from each side. And how do we do that? We subtract the measure of angle 2 from each side. So to do that, we cite the subtraction property of equality. And then to say their measures are equal, therefore they're congruent, is to evoke the definition of congruence. The good thing about this being a video is that you can go back and watch this a second time if you need to. And if you do need to, then by all means go ahead. But I'm going to move on to the second theorem, which we are going to be talking about. The right angle congruence theorem, or the right angle theorem, I've also seen it called. And it works this way. Angles 1 and 2 are right angles. The thing we want to end up proving is that they are congruent, which is easy. We can see the steps right here. 1 and 2 are right angles, given. That's 1/5 of it, right? These two are the same. If we know that they're right angles, then they measure 90 degrees. That's just saying that's what it means to be a right angle. That's the definition of a right angle. A right angle is one that measures 90 degrees. So to then say that the measure of 1 equals the measure of 2, I'm hoping you can figure it out in your head how I bring these two together to get me this statement. And that is, again, either substitution or transitivity. And then to say their measures are equal, therefore they're congruent, is the definition of congruence. By the way, definitions are biconditional, remember, so in another problem, if I wanted to, if it served my purposes right, I could say these two angles are congruent, therefore their measures are equal. So I can go from line 4 to line 5, or line 5 to line 4, depending on my needs, if I ever want to evoke this definition. But we're done here. That was easy. Let's next look at the congruent supplement theorem. We're looking at 1 and 2. 1 and 2 are supplementary. Angles 3 and 2 are also supplementary. I've tried to scale them in such a way that it looks like that's the case, but just take my word for it that 2 and 3 are supplementary. You can kind of tell that 1 and 2 are supplementary based on the fact that they almost make a linear pair. Like if I moved this angle over a bit, then it would be a linear pair. But anyway, we're going to just assume that this is true because I told you so. Don't whip out a protractor. Let's just pretend that it's true. So then to say that 1 and 2 are supplementary, and also 3 and 2 are supplementary, implies that we have these two equations. The sums of each angle pair is 180 degrees. That is, again, the definition of supplementary. If someone asks you, if you tell them that these two angles are supplementary, and then you say that their sum is 180 degrees, and they ask you why, you say, well, that's what it means to be supplementary. It means that their sum is 180. So to go from this second line to this third line, I'm essentially taking the two parts of it and pushing them together. Essentially, again, green quantity is equal to 180, other green quantity is equal to 180, so I guess the green quantities are equal to each other. And now we're seeing parts of this proof that look a lot like parts of the previous proof, right? Where what we just did is substitution or transitivity. What we're doing here is essentially subtracting the measure of angle 2 from each side, so if we want to justify how we can do this, that is the subtraction property of equality. And then again, to go from equal measures to congruent shapes is definition of congruence. I'm going to breeze through the next one because this being the congruent supplement theorem and the next one being the congruent complement theorem, very little has changed. I mean, we changed some words around, and then we changed the sum of the measures to 90 degrees. So we would expect all the steps to be the same, right? Given definition of complementary this time, not supplementary. But then everything else works the same way. I took these two, put them together via substitution or transitivity. I subtracted the measure of angle 2 from each side, and then definition of congruence. Great. Here's one for practice. That again, if you want to pause it and try it, that's cool. But I'm just going to power through it. And then we should be done after this, I think. I think that'll be sufficient for today's lesson. Given 1 is complementary to 2, 2 is complementary to 3. Don't think like transitivity here, like if 1 and 2 are complement and 2 and 3 are complement, then therefore 1 and 3 are complement. Transitivity is an equality property, which is to say transitivity works with equality. It also works with congruence. It doesn't work with complementary angles. It may or may not work with parallel lines. It doesn't work with perpendicular lines, which is to say, like, if line A is perpendicular to line B and line B is perpendicular to line C, that doesn't mean, I should say, that A and C are perpendicular to each other. So be aware of the limitations of our theorems and conjectures. But anyway, enough of that. This is given to us, cool beans. We can skip all that other stuff. Like the fact that we justified the congruent complement theorem means that we don't need to go through all the steps to justify why 1 and 3 are congruent now. We can just cite the theorem. We're essentially taking a shortcut. We can use the theorem as a shortcut, as like a summary of a bunch of other steps. So here's what I was talking about before, where I can go from the shapes are congruent to their measures are equal. If I want to stop talking about the shapes and start working with some numbers and actually start doing arithmetic with their measures, I can say that this is the definition of congruence that brings me from one to the other. And again, the definition of congruence could bring me back if I wanted to, because it's a biconditional sort of statement. But anyway, at this point, the measure 1 is this. The measure of 3 is the other quantity. So I'm kind of hoping you can see that what we've done is substitute green for green, blue for blue. Therefore, that's the substitution property. I don't think you can get away with calling it transitive this time. Mainly because I substituted 2 parts. It wasn't like there was 3 quantities and I related them all together. It was just swapping a couple parts on each side of the equation, so straight up substitution. And then from here, however you want to solve it, like there's more than one way, but I'll tell you what I did. I subtracted 5x from each side. Then I added 36 to each side via the addition property. And then finally, to wrap it up, I divided by 3, which is the division property. And then, folks, we're good. So thanks for sitting through these proofs. The homework associated with section 2.7 is actually very little proofs. I felt like we needed to see this, though. It's very much more about the implementation of these theorems for solving things, so I predict that you'll find it actually quite easy. So thanks for watching, and let me know if you guys need anything.